Hello, everybody. It's week 9. This is the last week of lecturing, and next week we'll start to see presentations of the final projects. And also, I want to update with you on the homeworks. So I apologize that I haven't graded homework 2. I don't have TA for this course, and lately it's been a lot of various stuff. So, but I'll get back to you on homework 2 on the grading sometime this week. And also homework 3, it will be shorter than past homeworks. It will be about causal DAGs and instrumental variables. And I will have that posted hopefully today, but the latest tomorrow. And as always, you'll have about 2 weeks to work on it. Okay, and any other questions before we get started?
Yeah, when does the report for the final due?
Oh, it's let me see. I put it in the let me find out. I put it in Canvas so that if you go to assignments, you'll see it. So yeah, so I wrote June the 12th. So that's, I think, a Saturday in the final exams week.
Okay.
And I also put up a place for you to upload the presentation slides. So I would appreciate if before each of yours presentation, you could send me a draft of your presentation slides, for example, like 30 minutes beforehand, so that I can take some notes. But the final version doesn't have to be submitted there. So I made the upload window to be the same as the final project report. Okay. So let's get started with today's material. So it's gonna be quite exciting, at least to me, because this is the most closely related to my research, but I think it will be very interesting to you as well. This would be the, I'd say, the most challenging topic of this course in this quarter. But we'll see how this goes. And as always, feel free to interrupt if you have any questions. Okay, so causal inference in longitudinal setting. All our previous discussions have been focusing on treatment at a single time. So usually it's called a cross-sectional data, where you have single time treatment and then you have an outcome after that. So I believe probably all of you have studied longitudinal data analysis here or there. You have probably heard of things like random effects models or generalized estimating equations. And if you haven't, that's fine too. Today's lecture does not rely on these knowledge. But in general, longitudinal data are data collected repeatedly on individuals over time. So we can have repeated measures of covariates and outcomes for each individual. And we can also have, in the causal inference context, repeated measure of treatments over time. So for example, we may prescribe different dose to a patient at different months over the course of a disease. So these are called time varying treatments. And the big question that we're going to deal with today is how to define, identify, and estimate causal effects with these time varying treatment settings. So a very brief literature review to help you know some of the big topics in the area. So the potential outcomes framework, it was formalized by Rubin in the 70s. And in 1986, Jamie Robbins published this paper, which extends the potential outcomes framework for longitudinal data setting. And then, a lot of these early works for time varying treatment causal inference was done by Robbins. So he proposed 2 very important models. One is called structural nested mean models that unfortunately we probably don't have time to cover in this class, but I have posted a optional reading I believe in module 3, because there is a counterpart of the structural nested mean model for the cross-sectional observational study as well. So that's one of the models, and the other model is the marginal structural model that we have seen. And today we'll see that this extends to the time varying treatment case as well. And then more recently, there has been work on dynamic treatment regime, or some of you may have worked on topics such as individualized treatment rules, etc. And these were, they stem from the computer science area of dynamic programming and reinforcement learning. They have been brought into statistics by Susan Murphy. And more recently, there has been work on mobile health and causal excursion effect, where for the longitudinal data, the number of time points is very large. So in today's example, we'll see, the examples that we see are 2 time point cases. So that's like toy example for longitudinal data. And on Thursday, we'll see that additional challenges arise when the time points is large and how to deal with that. Okay, so we'll be looking at 2 types of settings. They are not that different, but for the purpose of our discussion, I separate them as 2 settings. Usually in the literature, people don't really distinguish them. So the first setting is that we have longitudinal treatment, but we only have a single outcome measured at the end of the study. So this would be the data structure that we work with in setting 1. We have the x's, the time varying covariates. We have the treatments, the a's over time, and suppose total number of time points is capital T. Then at the end of the study, we measure some kind of outcome of the individual. And for this setting, we can use marginal structural models and parametric G formula. And in particular, there are extensions to longitudinal data, which we'll see today. And so these models would apply in this setting. There is another setting where for the outcome, it's also longitudinal. So at each time point, we have a covariate, a treatment, and an outcome. Right? At the second time point, we also have this kind of structure. So if you have studied longitudinal data analysis like GEE or random effects models, maybe the second setting is more familiar to you. But anyhow, this is another setting for longitudinal time varying treatments. And in this setting, the marginal structural models also work, and this other model, structural nested mean model, work as well. And we'll see on Thursday some related work in mobile health and causal excursion effect. So today, for today's course, we'll mostly focus on setting number 1, because it's, you can think of setting number 1 as a special case for setting number 2, actually. And towards the end of the lecture, we'll touch briefly upon setting number 2. Okay. So here's a reminder of the notation as well as some new notation. So xt is time varying covariate, at is time varying treatment, and we assume that the treatments are binary. Y is the outcome measured at the end of the study. So data from each individual, it looks like this, and where we have at the end, we have measured an outcome. So we assume that there are capital T total number of time points, where capital T is a known quantity beforehand. So it's not a random variable. But the methods that we introduced today can easily generalize to settings where you can have a TI for each different individual, right? You can have different time of follow-up for different individuals. But for notation simplicity, I'm just writing a single capital T. And as always, we are assuming individuals are IID. So although within individuals, obviously we have correlation because it's longitudinal data, but across individuals, assume they are IID. So some additional notation that will be useful for our discussion. This is a overbar notation commonly used in causal inference literature and also probably some other longitudinal data literature. So we use the overbar to denote a variable from the first time point up to little t, so up to this subscript little t. So this is a bar of t is this vector. And similarly, x bar of t is this vector. So covariates from time 1 to time t. And by the way, this x1 here is the baseline variables because it's measured before any of the treatment assignments. Another notation is the so-called history or observed history. We use HT to denote it, and it's essentially it is everything that's measured before AT. All the X's and all the A's that are measured before AT. And similar to cross-sectional settings, we also can define a propensity score. The propensity score would be the probability of assigning treatment conditional on the observed history. And sometimes we use this notation P sub t of H of t to denote the propensity score. Any questions? Okay, so having defined the observed data, now let's look at the potential outcomes for time-varying treatments. So because our outcome here in this case is measured at the end of the study, there are many treatment assignments that can affect this outcome, right? So the potential outcome is indexed by the treatment history, the entire trajectory of treatment assignment. So in other words, for each individual, we would have 2 to the capital T number of different potential outcomes. And again, only one of them is observed for each individual. So we can also have potential outcomes for the time-varying covariates. This is something that's different from observational settings. Because in observational, sorry, not for observational, but for cross-sectional settings. For cross-sectional setting, we only have a single time point, so there are no covariates after treatment. But here we would have covariates after the first treatment and also covariates after the second treatment, etc. So we can define the potential outcome of xt to depend on all the treatment assignment up to that time. And similarly, we could also have potential outcome for treatments over time, right? A treatment assignment at time little t can depend on the prior treatment assignments. So this would be the potential outcome of AT. Now, if you read the textbooks or literature, people usually don't write the potential outcomes for the treatment assignment, because usually the interest is not in the causal effect of previous treatment on the future treatment. But if you want to do that, that's technically, this is the correct way to do things. Okay, so having defined the potential outcomes, now let's look at
I have a question.
Yes.
Do people use the potential outcomes for the covariates pretty often?
Sometimes, yes. So on Thursday, you will see a situation where the potential outcome for the covariates actually matters. For today, no. For today, we will be looking at effect modification by baseline covariates. So the potential outcome for the covariates doesn't matter.
Yeah, because I was going to ask if it was based, it was time invariant covariate. You don't really care what the, how it changes.
Yeah. Yes. So for example, to elaborate on this point, just for the purpose of this class. So if xt is age of the person at time t, then it wouldn't be affected by the treatment, at least in the current science and technology. So in that case, the potential outcomes doesn't really matter because xt, the age under any treatment assignment, would still be the same. But sometimes if the time varying covariates can be affected by previous treatments, for example, disease progression or some other information, then conceptually it matters. So we should write as a potential outcome, not just the observed outcome. And then we'll need assumptions to linking that to the observed outcome. Okay. So now before we actually talk about causal inference methods, causal assumptions and methods, I'd like to introduce a very interesting issue called treatment confounder feedback. So here's the background. For single time point treatment setting, regression adjustments can actually provide consistent causal estimates if you have the correct regression model. We haven't really touched upon this when talking about a cross-sectional setting, but this is one of the methods to do causal inference, and you can find I believe a section on this in Hernan and Robins's book. The reason that this is not commonly used is because we would have to have correctly specified regression models. For example, if we have conditional ignorability and we have a correct model for this conditional expectation, then some parameters in this model can be interpreted causally because conditional on X, A is as if randomized, right? So we can use regression to estimate these causal parameters. Now, people don't usually use this approach is because having correctly specified regression models such as this is a strong assumption. So usually people use marginal structural models or doubly robust estimators or matching, all these other methods that we discussed. But the message for here is that regression adjustment is a possible or feasible option for single time point treatment setting. Now, for the time varying treatment setting, as we'll see today, we'll see that sometimes regression can never work, regardless of what variables you adjust for and what models you have. Like you can have the perfectly correct model, but regression still doesn't give you the causal estimate. And this issue is called treatment confounder feedback. So we'll see an example and then delve into more details of why there is this fundamental issue. And you will see that this all connects to a lot of the concepts that we have talked about earlier in this course. So let's consider a toy example with 2 time points. And suppose we don't have baseline covariate, just to make it even simpler. So suppose we are looking at a 3-month study. At month 1, we assign treatment to individuals. Well, we'll talk about how we assign these treatments on the next slide. But suppose at month 1, we assign treatment, we observe the treatment assignment. Then at month 2, we measure the disease progression, and we denote it as X2. So X2 would be a potential outcome, but we observe the X2 actually observed value. Then, based on the disease progression, we assign another treatment. So in cancer, the A1 would be the first line treatment, and A2 would be a second line treatment. So we assign another treatment at time 2. We observe the treatment assignment. Then at time 3, we measure a final outcome. So here is another cancer progression, but you can generalize this. So we call that Y, and this is the potential outcome of Y. So for this case, suppose A1 and A2 are both binary, 1 being higher dose, 0 being lower dose. And we also, for simplicity, suppose X2 and Y are both binary as well. And let's suppose 1 is the better outcome. Maybe 1 denotes slower disease progression. Okay, so this is the data we observe from this study. And we are assuming that at each time, the treatments are conditionally randomized. So let me explain a little bit more. So this is at the first time we randomize 50-50 to A equal to 1 and A1 equal to 0. Then among those assigned to A1 equal to 1, suppose all of them have outcome, intermediate outcome measure x2 equal to 1. So this is the time varying covariate at time 2. Then, so among these, then we further randomize with 25% receiving A2 equal to 1 and 75% receiving A2 equal to 0. And suppose this is the outcome that we observed for each of these groups. We have 60% in this group with y equal to 1. We have 50% in this group with y equal to 0. This is, I'm explaining the data generating distribution or the observed data. And you can think about the setting where we have a very large sample size, like infinitely many sample size. And similarly here, we have for A1 equal to 0 group, their outcome, their not outcome, but time varying covariate. Suppose that's 50-50, 50% equal to 1, 50% equal to 0. Then these two groups are further randomized at the second time point, and we observe their outcome. So this is how the you can think of this as how the observed data is generated. Okay, so now let's consider estimating a causal quantity. So one causal quantity would be the marginal causal effect due to a treatment sequence. So for example, maybe we can select A1, A2 and A1 prime, A2 prime to be different combinations of treatment sequences. And we take the contrast. So this would be a, you can call that average treatment effect, but that's with respect to the particular choices of these four A's. And this would be a typical causal estimate for such trials, where you have sequential randomization. Okay, so for example, let's suppose we're interested in the contrast of these two quantities, always taking high dose and always taking low dose. So are we able to use regression to estimate this causal effect? Let's see. So this is the goal, and the question, this is the causal DAG, that capturing this data set, right? We have A1, we have A2, we have two treatments. In between, we measure some intermediate time varying covariate. And then at the end of the study, we measure Y. And we see that A1 is randomized, A2 is randomized conditional on X2. That's what we see from the graph. Okay, should we adjust for X2? This is the question, if we want to use regression to estimate these quantities. Now, one opinion would be that we should not adjust or conditional on X2, because X2 is in the front door path between A1 and Y. In other words, it is an intermediate variable, right? If you still remember, we discussed in the causal DAG lecture that we don't want to block the front door path, because front door paths can carry information about the causal effect we care about. So suppose we do not condition on X2, right? So by saying we are running regression, in this case, we are essentially calculating the sample averages or the proportions. So we would be, if we don't condition on X2, we would be calculating this sample average and this sample average. So let's go back to see what these numbers are, right? A1 equal to 1, A2 equal to 1, and A1 equal to 0, A2 equal to 0. Okay, so A1 equal to 1 and A1 equal to 1. This is the only path that satisfies this condition. So we have proportion of Y equal to 1 being 60%. when A1 equal to 1 and A2 equal to 1. By saying when, I mean conditional on A1 and A2 values in the observed data set. Okay, another contrast is this part, A1 and A2 both equal to 0. So let's look. A1 and A2 both equal to 0 are here and here. And we have, if you look at all these paths, you will see that this path has 3 times the individual than this one. So therefore, this 80% and the 0%, they average to 60% because this part has 3 times the individuals. Okay, so what we get is 60% minus 60% when we're calculating this from the data, which is 0. So that's one answer for this causal effect if we do not adjust for x2. Now, another opinion is that we should adjust for x2 because it is in the backdoor path between A2 and Y, here highlighted in red. And we know that in this case, x2 is a confounder for the relationship between these 2 variables. So we should adjust for that, otherwise this relationship is confounded. So one way, well, I guess the only way to do this via regression would be to include x2 in the regression or in here in the conditional set. So let's see, if we, for example, if we look at x2 equal to 1, what do we see? What do we get? We can go back to the graph and find out these numbers. So let's actually go back to this graph. A1 equal to 1, x2 equal to 1, A2 equal to 1. That's 60%. So that's 60% over here. And the second part is A1 equal to 0, x2 equal to 1, A2 equal to 0. Let's see. A1 equal to 0, x2 equal to 1, and A2 equal to 0. That's 80%. Okay, so therefore we have 60% minus 80%, which is negative 20%. Now, you can also calculate a quantity for x2 equal to 0. Although in this particular example, this first conditional probability doesn't make sense when x2 equals to 0 because we don't have x2 equal to 0 on this path. But you can alter this, having 1% of x2 equal to 0 in this path, and then everything should go through approximately as well. But the main message to convey is that conditional on x2 and not, they get you different answers. Which one is correct? It turns out that neither of the approaches is correct. And as we'll see later on, the correct solution would actually be 20%. So it's not 0, it's not negative 20%. It is 20%. So what's going on here? Why is neither approach correct? The reason is because of the so-called treatment confounder feedback, which means that the treatment, an earlier treatment affects a confounder for later treatments, and the confounder affects this future treatment and also affects future outcome, so that it is a confound. Okay, so and we have seen this dilemma, right, on previous slides. On one hand, we want to adjust for x2. On the other hand, we don't want to adjust for x2. So because of this, regression does not work, because choosing either way isn't correct. And we'll see that we must use other approaches, such as marginal structural models or inverse probability weighting, etc., to deal with causal effect in this kind of settings. So if you want to know more about this topic, there are additional examples, for example, here in the Hernan and Robbins' book, and also this is also mentioned in the longitudinal data analysis book by Diggle et al. This is a classical book on longitudinal data analysis, which has nothing to do with causal inference, but you will see that the treatment confounder feedback actually has an interesting sibling in that situation. So you can check that out as well. Before we move on to the causal assumptions and estimation, any questions?
I have a quick question.
Yes.
I'm wondering, are you going to talk about the situation where you have multiple outcomes at different time points?
Yes, we'll talk about that towards the end of today.
Okay, thank you.
Mm-hmm. But to add up to that, you can imagine similar dilemmas would occur. Right? If you have a y in between, then you will also have
I agree.
This situation is not solved. So yeah, but yes.
Okay.
Any other questions? Okay, so causal assumptions. Let's as we have done in many of the earlier classes, right? We use potential outcomes to think about causal effect, to try to define causal effect. We have just defined one example. Then we'll see what are the causal assumptions that we would need in order to identify the causal effects. In other words, to write the potential outcomes notation into observed data. Then we can proceed to do estimation. So one causal assumption, or I guess a few of the causal assumptions, have to do with the assignment mechanism. And a lot of these have parallels in the cross-sectional settings. So hopefully a lot of these ring bells in your mind. So in single time point treatment, we have three types of treatment assignments. We have ignorable treatment assignment, or simply randomized. We have conditional ignorability, or conditionally randomized treatments. Then we also have unobserved confounding. So in the longitudinal setting, we'll see that we also have these three analogs, three different types of assignments. But of course, since there are multiple treatment assignments over time, so we can have a mix and match situation across these three for different time points. Now, on the next few slides, we'll see examples of different types of treatment assignments for the 2 time point situation. Okay, so this looks a little bit complicated and too much arrows, but we'll see what's going on and what's the important things there. But first, let's look at this cross-sectional setting. This is a ignorable treatment assignment. In other words, simply randomized, because there is nothing that have arrows pointing into A. Right? There are no backdoor paths to be blocked. So A is ignorable, conditional on empty set. You can have different ways to explain why this is ignorable. For 2 time point setting, suddenly the number of arrow increases by a lot, because all kinds of variables can affect each other. But what's important is that here, there are no arrows pointing into A1. So A1 is ignorable or completely randomized. And there are almost no arrows pointing into A2, except for an arrow from A1. And usually people think of this setting as also as ignorable, because the treatment, the impact of A1 on A2 doesn't confound the causal relationship, because we will always be we'll be conditional on A1, conditional with quotation marks, because we're interested in the causal effect of A1 and A2 on Y. Now, if we are only interested in the causal effect of A2 on Y, we're not considering A1 as a treatment, then this would be a confounded treatment assignment, and you will need to conditional on A1. But usually when people think about time-varying treatments, they will be looking at all the entire treatment trajectory, and therefore an arrow from A1 to A2 doesn't matter. What matters is the arrow from all these other variables into A2, which creates backdoor paths that we need to block. But here, since there are none of these, so here A1 and A2 are ignorable. That's one example. Okay, so this is another example. This is a conditionally ignorable treatment assignment. So in this case, we have X having an arrow pointing into A. So we see that there is, well, two backdoor paths, but it suffices to block X, right? So A is conditionally ignorable, conditional on X. An analog for time-varying treatment setting is here, where compared to the previous one, we have these three added arrows, the blue ones. And the blue ones means that the time-varying covariates affects the treatment assignment. So the treatment assignment are conditionally ignorable given the time-varying covariates. We will see a more precise definition of what's a conditionally ignorable treatment assignment, or in our case, we will call that sequentially ignorable treatment assignment for the longitudinal case. But hopefully here you get an idea of what are the important arrows. Okay, a third setting is when we have unmeasured confounding. So suppose U are the unmeasured variables. Then if we have an arrow pointing from U to A, then this backdoor path we're no longer able to block using observed variables. So therefore, we say that we have unmeasured confounding. And similarly for here, unmeasured confounding would occur if we have any of these red arrows. We have arrows from confounder to the treatment assignment. Okay, so having seen these three different settings and the relationship between single time point treatment and time varying treatments, let's be more formal in terms of mathematical notation. So we'll introduce the concept of sequential ignorability. This technically should be called sequential conditional ignorability, but usually the term conditional is dropped in the literature. And what people are referring to is the conditional aspect of the ignorability. Okay, so what it means is very simple. It means that at each time t, the treatment AT is conditionally ignorable given the observed history H of t. Remember, H of t are everything observed before AT. So in other words, if you relate to our ignorability definition in the past, it would mean that AT is independent of future potential outcomes given HT. So here is a formal definition. AT is sequentially ignorable. Usually people don't write conditional on HT because that's taken as given. If for every time point we have AT independent of these future information, future potential outcomes. So this would be the future outcome. The potential outcome of the future outcome. This would be the potential outcome of the future covariate. So here I should write from x little t plus 1 to x capital T, but it doesn't really matter because here we're conditioning on H of t. So the past covariates are absorbed in this H of t. So, but anyhow, this is the definition of sequential ignorability. The important part is this is defined sequentially in time. This is also called sequential exchangeability in the literature and also in Hernan and Robbins' book. And again, conditional term, the phrase conditional is almost always omitted in the literature. Any questions? Okay, so remember we have there are three assumptions that usually come together: conditional ignorability, sutva, and positivity. And similarly, we will require these assumptions here. So this is the sutva assumption, or the so-called causal consistency assumption. It is saying that the potential outcome under observed treatments is the observed outcome. So this actually is very similar to what we have seen in the past, right? The potential outcome under the observed treatment trajectory is the observed one. And for covariates, we also have similar sutva results. But because we have time-varying covariates, the sutva result needs to hold for all little t. So in other words, this is assuming there are no interference and no hidden variation of the treatments. Okay, so technically, we also need to have sutva for the treatment indicator. So for example, we would need assumptions like this. So the treatment at a second time point, that potential outcome given observed treatment at the first time point is the observed treatment at the second time point. Then the potential outcome of this one given this potential treatment assignment, where the potential treatment assignment is itself a potential outcome, when we then change everything to observed, it becomes the observed. So you will have a whole lot of this for all the treatment assignments, but usually people don't write this. Like what we're writing here, right? This should actually be expanded to the iterated version of all these parentheses, etc. But that's not, that's just a technical issue. That's not a conceptual difference. Okay. Then we also have this assumption of positivity. Again, this is almost the same as what we have seen before. At each time, the true propensity score is always between 0 and 1. So we always have probability to assign a equal to 1 and also assign a equal to 0 at any time for any covariate or history information value. This is the formal statement of the positivity assumption. Any questions about, yes?
Yeah, of course. Is this assumption true for all the methods we're going to use?
Are you asking, do we require this assumption to be true for all the methods?
Yeah.
So for today, we actually will see, well, today we'll see a few methods, and yes, this is required. And for Thursday, I believe this will also be required. So the answer would be yes, we would require this positivity assumption. Do you have some method that does not need positivity assumption in mind?
Yeah, maybe like an instrumental variable method. You have a time varying instrument.
Ah, I see. Okay, I'm not really familiar with that, so I can't say yes or no. But that's an interesting point. But at least for what we're going to talk about, we need this.
Yeah. Certainly for like, the main stuff. Okay.
Right.
Cool.
Okay. You're 2 ahead of me, but that's fine. That's good. Okay. So, so now that we have talked about causal assumptions, let's talk about identification. So how do we identify causal effects? We haven't really defined what is the causal effect we care about yet. We haven't really said, oh, this is the ATE for longitudinal data settings, but we kind of hinted upon it. We're not going to do a formal definition for ATE because that's kind of hard to define. when you have time varying treatments, it's hard to pin down to a single quantity. But in general, the causal effects with time varying treatments would be some contrasts about all these potential outcomes. So maybe you pick two of these potential outcomes, you take the difference, you call that a causal effect, or you can do some other modeling, as we'll see later on for marginal structural models. But the task for this part is, how do we identify the expected potential outcome for any given treatment history AT bar? So a notation is that this times t business is just repeating the Cartesian product for t times. So this is our goal. How do we identify this quantity? And it turns out that the two identification results that we have studied, standardization and IPW, both have generalization to the longitudinal setting. So again, for simplicity, we'll first consider t equal to 2 case. We'll do a mini proof, and then I will show you the result for the general t, but I won't do any proofs there. If you're interested, you can try yourself, use mathematical induction to prove the general results. Okay, so let's look at standardization for t equal to 2. In this case, this is the data we observed. 2 time points, then an outcome. And we're assuming Sutva, positivity, and sequential ignorability. So how do we identify this average potential outcome? Okay, so I'll just do the derivation as I explained. So first, we can do the iterated expectation conditional on x1. Then after conditional on x1, because we have sequential ignorability for a1, we can put a1 equal to little a1 in this conditional expectation. Right? So first we have only x1 without this part. That's just the law of iterated expectation. Then we can add this in due to sequential ignorability. But this is not done yet. We still have this potential outcome here. And we need to do something with A2 in order to use Sutva to get rid of the potential outcome. So this is what we do. We look at this inner expectation. This is copy pasting it over here. Let's do another round of iterated expectation. Let's do iterated expectation given x2. So this is conditional iterated expectation. I'd say that's the terminology. And I believe I have posted a discussion on the discussion forum of Canvas, so you can check that out for some more discussion on this probability result. So now we have this. Then we look at here. We have all the history variables for A2. And therefore, given this set, we have sequential ignorability for A2. Therefore, we can just add A2 into this conditional set without having to change anything, because A2 is independent of this potential outcome given x1, a1, and x2. Right. Okay, so now we have a1 equal to a1, a2 equal to a2, and the potential outcome of a1 and a2. So we can plug these in. We can replace this little a1 by capital A1, little a2 by capital A2, and then we can invoke Sutva to replace this potential outcome by the observed outcome. Okay, so this is what we get for the inner part of this expectation. And therefore, putting back the outer expectation, we have this result. This is the standardization result. Expected potential outcome is a lot of iterated expectations, but first conditional on x1 and a1, then conditional on both x1, a1 and x2, a2. Okay, so let's see how do we use this result in our previous toy example. What do we get? What is the expected y00 using standardization? How do we calculate from this graph? So let's calculate this quantity. And here I'm just repeating the standardization result, but because here we have no x1, remember, in here we have no x1 in the graph, so it simplifies this. We remove x1 in both of these expectations. So the goal is to calculate this quantity. How do we do that? Now let's first look at the inner part. So we can calculate this for different values of x2, right? This is just a conditional expectation on observed variables. So we can read this off directly from the graph. For example, 0, x2, 0, right? So we have a1 equal to 0. Then suppose x2 equal to 1, a2 equal to 0. Then we have expected y given this 3 variables being equal to 80%. That's this. That second situation, a1 equal to 0, x2 equal to 0, a2 equal to 0. So we have 0, 0, 0. This is the only path. And the expected y conditional on these 3 variables is 0. So this is 0%. So having figured out the inner expectation, the outer expectation is integrating over the distribution of x2 given a1 equal to 0. I'm just reading off the integration or the expectation from this formula. Okay, so in order to do that, we need to calculate the probability or the distribution of x2 given a1. And that we can do given a1 equal to 0, because we know that when a1 equal to 0, we have 50% chance of x2 equal to 1 and 50% chance of x2 equal to 0. This is the observed variables. This here is not a randomization. Okay, so therefore, this probability is 50%. Now, having calculated these quantities, we can assemble them to get the entire expectation. So the entire expectation would be this first part times probability of x2 equal to 1 given a1 equal to 0, as in here. So that's 80 times 50. And the other part, when x2 equal to 0, this inner expectation is 0. And for completeness, the probability of x2 equal to 0 and given a1 equal to 0 is 1 minus 50%. So this is the result for expected y00 using standardization. Any questions? Okay, so we have done one calculation. Similarly, we can calculate all these other quantities. And in particular, this first one is very simple. y11 would be replacing all these with zeros with ones. And you will see that we only have a single path with all these being equal to 1. And therefore, this is actually just 60%. There's no averaging over different kind of things business. And so therefore, the causal effect that we were talking about in the treatment confounder feedback section is 60% minus 40%, which is 20%. Now let's see, how do we generalize this procedure to arbitrary number of time points? So this first line, this is still the standardization result that we have. Now, another way to write this, instead of writing a lot of expectations, it's to write out as if the x's are discrete random variables. So, for example, the this inner expectation, this is a expectation over y. So we're not able to further simplify that. So we just copy paste over here. Now, for this expectation, this is integrating over x2 given x1 and a1 equal to a1, right? So we can multiply by the probability of exactly this thing and sum over x2. So this part here is the thing without the outermost expectation. Then the outermost expectation is integrating over x1. And that's an unconditional distribution. We're not having any additional conditions in this most outer expectation. So this is just integrating the marginal distribution of x1, which we can write over here, the marginal distribution of x1, then summing over x1. So this is another way to write the standardization for t equal to 2. Now, for general t, you can kind of see the pattern. You can imagine that this inner expectation getting longer and longer with more and more variables. So usually the G formula or standardization is written in terms of discrete x. So how do we generalize this? This is the general result. Again, we have a conditional expectation for y. Then we iteratively integrate over all the past xt's, given the history with respect to the xt's. After this class, you can verify yourself this formula, and you will see that when t equal to 2, this is exactly that. I'm just clumping a lot of these the multiplication of these probabilities together to this single product. And in here, I'm using the notation of little f, which is the conditional probability mass function. So is xt given these variables, just as it appears. And when xt is not discrete but continuous, you can replace the summation by integral, and that's it. So this is the general formula for standardization. Before we move on into inverse probability weighting, any questions? Okay, so for inverse probability weighting, again, we start with a 2 time point situation. So this is the data, and again, we're assuming these assumptions. How do I identify this quantity? So I'm kind of doing a backward engineer here. I know the result. I'm trying to minimize the derivation that I have to present, have to show you in order to convince that this is the correct result. So I'm starting from this conditional expectation. You will see that this conditional expectation is actually inside in here, is it the core part of the standardization. So let's start with this. If you're familiar with IPW ideas, you know that we can insert a IPW weight. We can insert a indicator of the treatment divided by its propensity score inside of this expectation, and then removing this conditional part. So to verify why this equality holds, let's look at this. So this expectation can be expanded to further conditional on A2, then times the probability of A2 given all these variables. Because we have this indicator, so when A2 equals to little a2, this is non-zero, and the probability we need to multiply cancels with the numerator. When A2 does not equal to A2, this is 0, so there's no term left. So therefore, you can see that these two terms, they equal to each other. And this is actually the same idea we have used in IPW previously multiple times. Okay, so building upon this, let's see what do we have. So this is the standardization result, right? And we have just manipulated the innermost expectation. So we replace this thing over here. Now, oh, there's another step. So first we can replace this, we can plug this inside here. Then we see that this is x1, a1 equal to a1, and x2. This is x1, a1 equal to a1. And therefore, we see a iterated expectation of x2. And therefore, we can get rid of x2 and get rid of the iterated expectation. So this is what we get after plugging this inside that. Okay, so now from here, we see that, oh, we have a1 equal to little a1. And using the same trick, we can replace this conditional expectation part with an IP weight. So we have indicator a1 equal to little a1. And in the numerator, we add another thing, probability of a1 equal to little a1 given x1. Then we can show that after plugging in this thing, we can remove a1 equal to little a1. So what's left is expectation of something given x1, then an outer expectation. So again, using law of iterated expectation, we can get rid of x1. So this leaves us with this final term, which has no conditional expectation, but two parts of inverse probability weights. Okay, so this is the IPW formula, identification formula for this kind of expectations for the potential outcomes. Now let's see, how do we use the IPW? Let's use this result to calculate the same quantity in our toy example and see how that, it should be equal to the standardization result, but let's just verify. In order to calculate IPW, you can imagine we will be writing down weights on this column, new column. So one thing that we need to do is to calculate the probability of people going through each path. So for example, here starting out, we have probability 1, then we have half the probability going to a equal to 1, half the probability going to a equal to 0. Here, everyone is x2 equal to 1, so we still have half the probability. Then after that, we have 25% and 75%. So we have a 1/8 of the original population going into this path. And we have 3/8 of the original population going into this path. And similarly, we can calculate these numbers. So these would be the weights or the proportion of the entire population that end up in these categories. And the proportion or the expected Y are calculated with respect to these subpopulations. So having calculated these weights, we can move on to calculate the IPW result for this expectation. So here I'm just rewriting the IPW result, but again, it simplifies because in this particular example, we don't have x1. So we have expected outcome multiplied by 2 weights here. So let's calculate these weights for each of these paths. Then we can, the outer expectation would be taken over these proportions. Okay, so when we look at these IP weights, we see that in order for the indicator to hold, the A2 would be the 0, A1 would also be 0 here, in order for these two indicators to be non-zero, the paths with non-zero IP weights are these with A1 equal to A2 equal to 0. So there are actually only two paths that satisfy this, A1 equal to 0 and A2 equal to 0 here, and A1 equal to 0 and A2 equal to 0 here. So let's calculate the IP weights for these two paths and then average them with respect to these red proportions. So let's just do that. So for the path resulted in 80%, which is this path over here, let's calculate this term and then that term. So probability of A2 equal to 0, given that, is A2 equal to 0, given these two, is 75%, right, compared to this 25. So this condition on that is 75%. And similarly, for the path here, we can also calculate a proportion, which is a quarter. So we have calculated this thing. Then we also need to calculate this. And this is a half because A1 is 50-50 randomization. And therefore, this expectation can be calculated as follows. So we're calculating averaging over these two paths with these proportion or these weights, but with this additional IP weights. So we're first, this is the proportion of y equal to 1, this is the proportion of y equal to 1 for each of these two paths. And then multiplying with the IP weights, and then these red numbers are what the expectation represents. So therefore we get 40%. Okay. So now let's look at the general T case. I'm just going to present you with the final result. So this is our IPW for 2 time point case. You can imagine that you will have more and more weights with general T. So in general, people would write something like this. So the expected outcome under a treatment trajectory equals the observed outcome multiplied by an IP weight, where this weight is defined as this. So the numerator is indicator of actually following this potential trajectory, and the numerator are the probability of following this trajectory. So the idea is the same with the IP weights for the observational study case. Now here I'm using omega because I want to distinguish from the W that will be used in the marginal structural model estimation. If you still remember, in cross-sectional settings, we also have IPW weighting for identifying a expected potential outcome, and we also have another version of IPW weights in estimating marginal structural models. These two weights are different because they were for different goals. One is for identifying a mean potential outcome. The other is for estimating a parameter in a marginal structural model. In the latter purpose, we are trying to reweight the population so that we have unconfounded treatment assignment. And we'll see what the weight would be for marginal structural models in this setting. Okay. Marginal structural models. This is a review for single time point treatment. So this is what we have seen, right? Simple marginal structural model. And we have also seen marginal structural model with effect modification, where V is a subset of the baseline covariance. And we have seen that the weights that we can use in estimating marginal structural model parameters is something like this. So if AI equal to 1, then you have this inverse weight. AI equal to 0, then you have this inverse weight. Now, I'm going to introduce some new notation for, I guess, equivalent ways to characterize the weights, because these new notation will be helpful to succinctly represent the IP weights when we have general T. So this weight is in fact this one if we think about the capital A as the set of possible treatments, which is 0 and 1, then this thing, I'm just rewriting it as this probability time powered to the indicator of AI equal to little a. Right? These are the two terms are exactly the same as these two terms. Now, another way to write this is using this notation, where we define little f of a given x as this probability. So you can think of f as a density or a probability mass function. Okay, so you can think about f taking f of 0, x, and f of 1 given x, and these two sum over to 1. Now, how does this equal to that? You can check the value individually, but another way to look at this is to view this quantity f of capital A, which is a random variable, as the probability of getting the treatment one actually gets. Right? If one gets A equal to 1, then this is the probability of getting A equal to 1. If one actually gets A equal to 0, then this part is 0, then this is the probability of getting A equal to 0. And therefore, this is the probability of getting the treatment one actually gets. Here, A is stochastic. We'll see that this notation being used in the general IP weighting for marginal structural models. Okay, so now let's move on to marginal structural models for time-varying treatments. So let's first consider setting number 1, where the outcome is only measured at the end of the study. So this is the data we have. A marginal structural model in this case is a model on the expected potential outcome under a specific treatment trajectory. So here I'm using a general notation using mu. So mu would be a function of the treatment trajectory as well as some unknown parameters. So you can imagine this can be linear or exponential or some other functional forms. And how the AT bars is incorporated into this could also have different ways. You probably know this very well now. This is different from this condition expectation of observed variables because of the possibility of confounding unless every AT is simply randomized. Okay. Now, we have also talked about marginal structural models with effect modification, and we have a similar version here for time-varying treatments. So again, suppose V is a subset of baseline variables. So V is a subset of X1. Then we can put a model on this condition expectation. Again, I'm using the same notation mu, but it can have a different functional form. One important aspect is that this type of marginal structural models can only include baseline variables as effect modifiers. They must not include time-varying covariates in V. So this is a little bit related to what Roy was asking about the potential outcomes of the time-varying covariates. So here, that's not used in here. We are only looking at baseline covariate effect modifications. And this is actually what the name marginal structural model comes from. This is marginal because it is with respect to post-baseline confounders. Okay, so estimation for parameters in the marginal structural model, as you might have imagined, is similar to the marginal structural models we have studied before. Again, we will be using weighted GLM, and the weights are the estimated IP weights. So this is the particular form for marginal structural models with time-varying treatment. Assume Sutva, positivity, and sequential ignorability, and a correct marginal structural model, then we can form this kind of estimating equations. So here is a residual. This is a derivative term. And in the middle, we have a weight. What is this weight? It is, I think the second role may be easier to explain. But the first role is a more precise and unambiguous notation. But let's look at the second role here. So for each little t, this is the probability of receiving the AT that you actually received, conditional on the observed history. Right. So for different ATs, this for AT equal to 0 and AT equal to 1, this probability would be different, and these two would sum up to 1. So now this entire product can be interpreted as receiving the treatment trajectory that you have actually received. Now that's with a caveat, because we are sequentially conditioning on all the x's, so we are not taking into account that the x's can be changed by previous treatments, and they can affect future treatments. But this would be one way to understand this denominator term. So if you find this way of writing things a little bit confusing, which I admit that I was when I first started reading some of Robin's papers, then this is another way to write the IPW weights. And here, the AT is the set of possible treatment values at t. And in our case, we're considering binary treatments always, so these would always be 0 and 1. Okay. So here I just want to give you one example, and more importantly, a very good reference for you to read for marginal structural models in time-varying treatment setting. So here, the researchers are interested in the effect of time-varying treatment on survival time, and they actually used a Cox proportional hazards model with a marginal structural model. But for our purpose, let's suppose the outcome is continuous. The key message I want to share with you is that in there, they assumed that y depends on the cumulative treatment received. So in other words, they're imposing models like this: expected potential outcome equals beta 0 plus beta 1 times the sum of past treatments. So this can be interpreted like a dosage. And in this case, an effect modification model might be something like this, or you can also have interaction term between V and the sum of the treatments. But of course, this is a very strong assumption. One could also use other ways to model how the potential outcome depend on the treatment history, not just this simple sum, but maybe some more flexible functions. So we'll have to end it here for today. Starting from next time, we will look at a second setting where we have longitudinal outcome as well, and how do we do marginal structural models for this setting, and also some some other causal inference methods for time varying treatments. Okay, thank you.
Thank you.